Thank you, Claudio, and thank you, Milton, for the invitation to speak. What I'm going to talk about is directed polymer in a random environment, and this is joint work with Stefan Jung from Tokyo. Okay, so let me introduce the model. So directed polymer in a random environment, it's a model of statistical mechanics. So the game is basically we are going to fix a state space and define the probability measure on this state space. So the state space we consider here is the set of nearest neighbor paths with n steps starting from 0 on ZD. Okay, so this is the omega n here. Because you have 2D choices for each step, and the choices are independent, the cardinality of this space is 2D to the power n. Now we are going to define a probability on this state space. And the first step to do that is to define an energy functional, and this energy functional, in terms, it's defined in terms of an environment. So what I mean by environment, it's really a bunch of numbers that are indexed by time and space. So we are in a discrete setup, so time is the set of natural number and space is ZD. Okay? And the energy corresponding to a path x, well, it's the sum of the omegas taken along the graph of the path. Okay, so the graph of the path x, so the set of nxn, it's the relevant object here. Okay, and now, given omega, we define the polymer measure for inverse temperature beta. So I haven't written what beta is, but beta is just a parameter, a positive number. Well, it's the probability measure on omega n that to each x gives a probability which is proportional to exponential beta times the energy. Okay, if we were physicists, we should put a minus, okay, but let's not worry about that. And I don't put a minus so that I don't confuse myself in the computation. Okay, so when you write this as a probability, basically you need a renormalization factor so that if you sum over all x, you get 1, and this renormalization factor, we call it partition function. Okay, and I told you that omega is a bunch of numbers, but we are going to choose the numbers in a specific way. So omega is really the fixed realization of a set of IID random variables. Okay, and we call blackboard P the probability associated with this omega. Okay, but generally you can think as omega as fixed, and you look at the polymer measure given omega. Okay, so this is just some illustration. Okay, so here it's in d equal 1. So this is somehow a polymer trajectory, so the graph of the nearest neighbor path. Basically the energy of this trajectory is just the sum of the omegas collected along the trajectory. And basically this means that each time you visit a given site, you multiply the weight of the trajectory by a factor exponential beta omega. Okay. So now what we are interested in is the typical behavior of the trajectory under the polymer measure. And in particular, we are interested in how this behaves asymptotically when n goes to infinity. And it turned out that to study this question, you can find a lot of elements to describe this, just looking at the partition function. So somehow some information on the system is encoded in the renormalizing factor that we had on the previous slide. And more precisely, we are going to be studying the renormalized partition function. So instead of taking z, we are going to take z divided by its expectation, where here expectation is taken with respect to omega. Okay? So the expectation of z, it's not something which is complicated to compute. Well, it's z is a sum, so you can just put this sum out of the expectation. And then when you look at the expectation of exponential beta times the energy, when you have fixed a path, the energy is just a sum of IID random variable. So what you get is it's just the Laplace transform of one of these variables to the power n, because they are all independent. Okay, so this gives us a way to rewrite Wn. Basically, to take care of the factor 2d to the n, well, you just put it on the denominator. And to take care of the Laplace transform, you define lambda beta as the log Laplace transform. Okay, and you subtract it in the exponential. So you subtract n times lambda beta. Okay, and now when we have done this rewriting, you can see that what we are really doing is we are making an average over x uniformly chosen in omega n. And it's the same thing as taking the expectation with respect to the simple random walk. Okay, so now in the next slide, x is just going to be the trajectory of an infinite simple random walk, okay, with infinitely many steps, but only the n first steps have physical relevance. Okay, so why is renormalized partition function nice? Well, it's a sign of this is this observation of Bolthausen that this sequence is a martingale when you equip your space with a natural filtration associated with omega. So Fn is just the sigma algebra generated by the omegas up to time n. Okay, so why is it a martingale? Well, simply when you take omega n plus 1, okay, here you have a sum going up to n plus 1. Then if you take the conditional expectation with respect to Fn, basically you see that the last term in the sum, it's independent of Fn, and all the rest is measurable with respect to Fn. So you just average with respect to the last term in the sum, and when you do this, you get the Laplace transform, and the lambda beta cancels it. So this is how you prove that this is a martingale. Okay, and it's a non-negative martingale, so for free you have that it converges to some limit. Okay, and if you think a bit more about it, you can see that either this limit is equal to 0 with probability 1, or it's strictly positive with probability 1. Just because the event that the limit is 0, it's something which is measurable with respect to the tail sigma algebra. Okay, you have to take care to be a bit careful when you check this, but this is not difficult. Okay, so this justifies the following dichotomy. When the limit is positive, almost surely we say that we have weak disorder, and when it's equal to 0, almost surely we say that we have strong disorder. And a way to justify this terminology is, well, just thinking about what this means. So weak disorders, it really means that Zn behaves like its expectation at first order. Okay, that Zn divided by this expectation, asymptotically, it converges to something which is non-zero. Now, if you look at, okay, so let's look back at Zn. So Zn, it's a sum of Gibbs weights, and these Gibbs weights, they are, the exponential of the sum of IID variables. So each of the Gibbs weights, typically, it's much lower than its expectation, because you know that the exponential of the sum of IID variables, typically, it's much lower than its expectation. When you have weak disorder, it means that by summing over all trajectories, basically, you manage to average things out, and after taking the sum, things behave like their expectation. So it kind of tells you that in spirit, each trajectory brings the right contribution to the partition function. And this kind of indicates that your measure shouldn't be that different from the uniform measure in some sense. Okay, so this is a bit far-fetched, but this makes sense. So in this case, there is no disorder. So it looks like there is no disorder. In some sense. Okay, and well, when you have strong disorder, of course, this means that Zn is typically much lower than its expectation, so that averaging over x is not sufficient to make things average out. Okay, so basically you have strong disorder when you have no weak disorder. Okay, and what has been proved is that in fact there is a phase transition in beta. So there is a beta C that separates a weak disorder phase from a strong disorder phase. So when beta is strictly smaller than beta C, you have weak disorder, and when beta is strictly larger than beta C, you have strong disorder. So this was proved by Comets and Yoshida in 2006. Well, this phase transition might be trivial. There are two ways that it might be trivial. I mean, beta C can be either equal to 0 or infinity, but okay, I will not discuss about beta C being equal to infinity because this is something which is not, well, it's very well understood and it's not very interesting. But, okay, so beta C equal to 0 is something more interesting for our purpose. And what has been proved is that beta C is always strictly positive in dimension 3. So this was remarked in the 80s. And that beta C is equal to 0 in dimension 1 and 2. And this was in the early 2000s by Carmona-Hu and Kometsuchiga-Yoshida. So the moral of this is that in dimension 1 and 2, you have no phase transition. You have strong disorder at every temperature. And in dimension 3 and more, you have a phase transition. Okay, under some assumption of the distribution of omega, but I don't want to go into this. Yes?
So what happens at beta C?
And this result does not tell you what happens at beta C, but I will come to that later. But as far as these people are concerned, in this paper, they say we don't know what happened at beta C. Okay. So now let me tell you what weak and strong disorder mean in terms of trajectory behavior. So what has been proved is that in the weak disorder phase, if you look at the distribution of your trajectory, but you renormalize it diffusively, so you renormalize space by square root of n and time by n, then it converges to the distribution of a standard Brownian motion. Okay, there is a factor square root of d, but which is just there to match the variance to that of the random walk. Okay, so this means that on a large scale, you don't see the effect of the disorder. Okay, and the important thing is that here, like, this convergence holds for a fixed beta, okay, in a sense. So, yes, you don't see a dependence. The Brownian motion that you get here is independent of the environment. Okay, and well, this was proved in this form by Comets and Yoshida, but there were earlier results pointing to that direction. Okay, in strong disorder, it's a bit more difficult to state exactly what happened, but okay, let me try. So in the strong disorder phase, Wn goes to 0. So log 1 over Wn goes to infinity. Okay? And what Carmona-Hu and Kometsuchiga and Yoshida have proved is that, this thing goes to, when n goes to infinity, this is asymptotically equivalent to the sum of the INs, where IN is the probability that two polymers sampled independently share the same endpoint. Okay, so if you think about it, let's say that dimension is larger than 3. For the simple random walk, okay, IN would be something like n to the minus d over 2. So the sum of the INs would be summable. Here, when you have strong disorder, the INs are not summable. So in some way, it indicates that the polymer measure is different from the random walk measure. But if you want something much stronger, you can look at the case where Wn decays exponentially fast to 0. So in that case, this means that the sum of the INs is comparable to n. Okay, so in particular, this means that a positive fraction of the INs are larger than delta. So this means that for a positive fraction of the time, the probability that two independent polymers share the same endpoint is positive. Okay, so this clearly contradicts diffusivity. Okay, so this indicates that the behavior is very different from the one of the simple random walk. Okay, so this kind of motivates the next definition. We are going to study more specifically not the case where Wn goes to 0, but the case where Wn goes infinitely fast to 0. Okay, and it turns out that, well, this is a standard thing to look at. People have looked at the free energy of the model, which is the rate of decay of Wn. So the limit of 1 over n log Wn. So if you think, when this f of beta is 0, it means that, log Wn does not decay exponentially fast. And when it's positive, then it means that it decays exponentially fast. When it's negative, sorry, it means that it decays exponentially fast. So, okay, people have shown that this quantity is well defined, that it corresponds to the limit of its expectation, and that f beta is continuous in beta. And furthermore, it has been shown by Komets and Yoshida that it's non-increasing. So in particular, you have a second critical beta that I will call beta C bar, which separates a phase where the free energy is 0 to a phase where the free energy is negative. Okay? And by continuity, here you know what happens at beta bar C. At beta bar C, the free energy is equal to 0. Okay, so when the free energy is strictly negative, we say that very strong disorder holds. And note that very strong disorder is something which is stronger than strong disorder, because if you decay exponentially fast to 0, then in particular you decay to 0. Okay, so so now here is the picture of what I've said so far. So a priori, you have 3 possible regimes. Okay, above beta bar C, you have very strong disorder. Then possibly you have a regime between beta C and beta bar C when you have strong disorder but not very strong disorder. And then below beta C, you have weak disorder. But it has been conjectured by okay, basically the people that have been introducing these quantities, that in fact the 2 critical points are equal, and that you have only one phase transition from weak disorder to very strong disorder. But okay, this has remained so far a conjecture, except in dimension 1 and 2. So okay, remember that in dimension 1 and 2, I told you that you have strong disorder for every beta. But it has been further shown by Komets and Vargas in dimension 1 and by myself in dimension 2 that you have, in fact, very strong disorder at every temperature. Okay, so furthermore, okay, there has been no consensus about what happens at beta C. Okay, there is a conjecture that beta C is equal to beta C bar. You know that at the critical point, you cannot have very strong disorder. But okay, people didn't know whether to predict weak or strong disorder at the critical point. And in fact, you can find both conjecture in the literature. Okay, so here is our result with Stefan. So we have worked with the technical assumption that the environment is bounded from above. Okay, we don't believe that the result is, well, means the result should be valid beyond this assumption, and okay, part of our proof, I mean, only a small part on the proof of the proof relies on this assumption. Okay, so what we have proved is that, well, beta C is equal to beta C bar, so you only have one phase transition, and at the critical point you have weak disorder. Okay, and I will spend the remainder of the talk trying to give a sketch of the proof of this result. Okay, so I told you that, okay, so yeah, a way to summarize this result is that really whenever you have strong disorder, you have very strong disorder. Okay, so this tells you both of these things because at the critical point, okay, you know that if you have strong disorder, you have very strong disorder, and you know that at the critical point, you cannot have very strong disorder. Okay, and I've written this as an equivalence, but in fact, one of the implications is trivial. So what you really need to show is that whenever you have strong disorder, you have very strong disorder. Okay, so I think some of you, including the organizer, have already seen this talk. So I've included a new result that was not present a couple of months ago. So we know a bit more about what happens at criticality. So Stefan has been working a lot in the past few years on understanding the asymptotic decay of the partition function. And we have refined together his results recently. And what we can show is that if you look at the distribution of the partition function in the weak disorder phase, then it decays like a power. The tail is power. And the exponent that you have, okay, it's always larger than 1 plus 2 over d.
So the braces don't have any meaning there?
No, I wanted to write belongs to 1 plus 2 over d infinity. And, okay, yeah, it's a mix between two things that would make sense. And in this way, it doesn't make sense, yes. Okay, and this 1 plus 2 over d value, it's not something arbitrary. It's, okay, there are some reasons why you cannot go below. But at criticality, we know that p star is equal to exactly this value. Okay, so why is it interesting? Okay, or why does it interest us? Okay, I mean, first of all, in statistical mechanics, people are kind of really into critical exponents. This is what they like. So this is one first reason. But the other one is that understanding how things behave at criticality might be of crucial help to understand how things behave a bit outside of criticality. So we believe that knowing about this, we might be able to predict the regularity of the free energy around the critical point. Okay, but for the moment, we don't have. Okay, we have a clue, but we don't know exactly how to do this. Okay, so let me try to give you some ingredients about how we prove that strong disorder implies very strong disorder. Okay, so you want to prove that, okay, you assume that you have strong disorder and you want to prove that, Wn decay exponentially fast. Okay, so one first thing is that, okay, the free energy is the limit of this thing, the expectation of the log. And the idea is that you can transform this log into a square root, okay? So, and you will see in this lemma why it's convenient to have a square root. So the way you can do this is just you say, okay, the log, it's the log of Wn, it's twice the log of square root Wn. Okay, and then you apply Jensen. Okay? So, and then you can say, okay, if the expectation of the square root of Wn decays exponentially, then my free energy has to be negative. Okay, just because of this inequality. Okay, the free energy is nothing but the limit of this, so it's smaller than the limit of that. Okay, so instead of showing that log W, the expectation of log Wn decays linearly, we have to show that the expectation of square root of Wn decays exponentially. Yes?
Just to, I don't remember well about that. So the Wn doesn't have higher moments, right? Or it could not have higher moments than above.
Wn.
So including the question.
Sorry?
Answer including the question for people for.
Yes. So you have to give the microphone.
No, you can.
Okay. What's the question? Sorry.
So the question is W and beta may not have moments.
Okay.
Second moment.
No. W and beta has every moment. Okay, under our assumption that the environment is bounded, W and beta is bounded by a for every n, it's bounded by a constant to the power n. Okay, so but the other moments they might explode exponentially, and the fact knowing that they explode exponentially a priori does not give you information. Okay. So what we are going to show is really that the expectation of the square root of Wn decay exponentially And okay, you know that if you have strong disorder, you already know that the expectation of the square root of wn goes to 0. What we have to show is, in fact, that it goes to 0 sufficiently fast, and sufficiently fast is just like a power of n. So there is some kind of bootstrap argument that tells you that if you decay like a power of n, or actually if for some n, the expectation of square root of wn is smaller than a negative power of n, then you know that it decays exponentially. So this argument here is due to Comets and Vargas, and I'm going to sketch it on the board because it's a nice argument. So okay, let's assume that that this is true, okay, that this thing is true, and let's prove that this implies very strong disorder. Okay, so n now plays a fixed role, and we are going to show that Wmn decays exponentially. In M. Okay, so if we show this, and we show that very strong disorder. Okay, so why is it the case? Well, if you look at Wmn, okay, so it's the expectation with respect to the simple random walk of exponential sum n equal to 1 to nm of beta omega n xn minus lambda beta. Okay, and then you can decompose this thing, okay, by just here telling where your walk goes after multiples of big N steps. Okay, so here we'll put the indicator that xn is equal to x1, x2n is equal to x2, xmn is equal to xm, and I will sum over x1, xn, okay, over zd. Okay, so the idea is to find a way to factorize our partition function in order to gain some kind of submultiplicativity. Okay, so now you see that okay, for sorry, xm. Okay, so when you look at this expectation, you're just taking the contribution to the expectation of walks that pass through fixed point. And the idea is that this will allow to factorize things because now the bridges of the random walk are independent. Okay, so we are going to write this as a product. Okay, and this is, okay, sum over x1, xm. And now I have the product from j equals 1 to m of, let's see, maybe j equals 0 to m minus 1. Okay. Here you have theta mj xj wn xj plus 1 minus xj. Okay, so here some definitions are missing. So wnx, it's just the partition function where you restrict to the endpoint being x. Okay? theta k z of omega, this is just omega. The environment omega, but you look at it seen from the point kz. So it's omega n plus k x plus z n in n x in zd. Okay, this is the shifted version. This is really like omega, but seen from this point. Okay. And okay, now theta applied to the partition function is just the partition function which corresponds to the shifted omega. Okay, and maybe it's not something you immediately see if you're not used to this kind of thing, but I guess it's believable, okay, that what you obtain here is really a product of partition functions. And, well, the transversal displacement of the partition functions corresponds to this, okay, and the starting point is this one. Okay. Now, the good thing is that you know that the sum of square roots, no, the square root of a sum is smaller than the sum of square roots. And you also know that the product of square root is the square root of the product. So combining these two things, you get this. Okay? And now if you look at these random variables, they depend on time disjoint slices of environment. So they are independent. Okay, so therefore, what you get out of this is that the expectation of W and N, it is smaller than the sum over x1, xm, times the product, or from j equals 0 to m minus 1, of theta mj, of the expectation of square root of wn xj minus xj minus 1. Okay, and by convention, x0 is equal to 0. And here I'm using translation invariance. I'm using the fact that this theta here, I can erase it when I take the expectation. Okay, just because you don't change the law of the environment when you translate it.
Sorry, do you need a probability of your indicator function somewhere?
No. No. Here you have the indicator function. It's not a conditioning.
Ah.
Okay? Okay, now you can reorganize this. Okay? You make a change of variable, you call this yj. Okay, so then summing over the x's is just the same as summing over the y's. Okay, this change of variable from x to y is bijective. Okay, and then you can refactorize, so what you get is really the sum over y of the expectation of w and y. And then you get this to the m. Okay, because once you sum over yj, I mean, what you have is really, in the product, you have m times the same thing. Okay, so if you want to show exponential decay, you just need to show that this is smaller than 1. Okay, and now, well, this thing, okay, you can restrict yourself to y smaller than n, because if not, I mean, these are the only terms that are non-zero. Okay, you have 2n plus 1 to the d. Okay, you have less than this, okay, because we are considering L1 norm, and I'm taking L infinity ball because this is easier to compute. You have 2n plus 1 to the d terms, and each of them is smaller than exponential square root of wn. Okay, I'm just taking a crude bound. I'm just saying that this is smaller than this. Okay, and therefore you get that if this inequality is satisfied, then you're done. Okay, so in practice, what this tells you is that in order to prove exponential decay, you don't.
Sorry, can you repeat the last step? I got lost.
Oh, I'm just saying that WNY is smaller than WN. This is the point-to-point partition function, and the way I've defined it with no conditioning, which is the indicator. It's okay. So this sum over ZD, it's really not a sum over infinitely many terms. It's a sum over finitely many of them. That's a bound on my number of terms. Okay. So yes, if this thing is smaller than 1, then this thing decays exponentially in M. Okay, so you only need to show this for one n, but in practice, what's the interesting consequence for us is that if you can show that Wn decays like a power of n, exponential, the expectation of the square root decays like a power of n, then it decays exponentially. Okay, so this kind of simplify what we have to prove. Okay, so the second ingredient involves the size bias probability. So Wn, it's a non-negative random variable which has expectation 1. So therefore, you can consider it as a probability density. And you can define a new probability on your environment which is absolutely continuous with respect to the original one, but for which the density is given by Wn. Okay, and what happens is that if you want to, you can bound the expectation of the square root of Wn by the probability, the square root of the probability of A plus the square root of the probability of the complement of A under the size bias measure. And this is true for any A. Okay, so, well, why is this true? Basically, it's just an application of Cauchy-Schwarz, okay? Here, in the square root of Wn, you can multiply by a function and its inverse. Okay, it's inverse, I mean 1 over this function. Okay, then you apply Cauchy-Schwarz. Okay, and then you get the expectation of f under the size bias measure times the expectation of 1 over f under the original measure. You take f, which is constant on R and its complement, and you optimize, and this is how you get this. Okay, what interests us here is that in order to show that we have exponential decay of this, well, you just need to find an event an, which is very unlikely under P and very likely under the size bias measure. And by likely, I mean, and unlikely is the same, I just mean that the probability of the complement decays like a power of n. Because then you can combine the two preceding results, and this gives you exponential decay. Okay, if both these square roots here are smaller than a large power of n, this is okay. Okay, so the remainder of my sketch of proof is we are going to try to find this event an. Okay, and now we have to think about what's more likely under the size bias measure than under the original one. And well, the size bias measure, I mean, it biases things by the size of Wn. So under the size bias measure, Wn is larger. Okay, so the event that we are going to look at will be of the kind Wn is large. The thing that we don't control very well the distribution of Wn, but we can control very easily its tail. So the probability that we can control very easily the distribution of its supremum over all n. Okay? If you take the tail of the supremum of Wn, it decays like 1 over u. Okay, so this is 1 over Lu, and this u here is 1 over u. Okay? So the interval is 1 over Lu, 1 over u. Okay? So what I mean is that you can control this probability here up to a constant. Okay, so how do you prove this? It's just an application of the optional stopping theorem. So, okay, recall that omega is upper bounded by assumption. Okay, so what you have is that in a given step, the Wn can change at most by a constant factor. Okay, this is where I will L confirm. The L depends on beta and on the distribution of omega. Now let's define tau u to be the first n at which Wn is larger than u. Larger or equal. Okay, and let's look at the expectation of Wn tau u. So by the optional stopping theorem, this is equal to 1. Okay, now I know that this is smaller than L times u. Okay, this is bounded by a constant, so I can apply dominated convergence theorem. Dominated convergence theorem, and make n tend to infinity. And what I get is that this thing, well, this thing here, it converges pointwise to W tau u times the indicator that tau u is finite. Okay, because if tau u is finite, well, this becomes stationary eventually. If tau u is infinite, this goes to 0, because we have strong disorder. This is our assumption. Okay, and finally, so what you get is that 1, well, this is upper bounded by Lu times p tau u smaller than infinity, and this is larger than u times p tau u smaller than infinity. Okay, this is really u up to a constant, so this gives us the result. Okay, so this is nice, but slightly inconvenient for our purpose. So the next step is really to reinforce this result. Okay, we have some information about the probabilities that the sup over n of Wn is larger than u. Okay, what the problem is that we don't know for which value of n the sup is attained. Okay, so we want to show that if you restrict the range, okay, by taking n at most a large constant times log u, then you still get a lower bound, okay, which is almost as good. Okay, you need to take the constant large when. Okay, so log u here is really the best you can do because, well, because of this you need at least log u steps, okay, to overcome the level u. But it turns out that, okay, if you want to grow big, you have to do it fast, okay? Because if you wait that the random walk spreads out, then you need to improve the environment on many places, and this costs more. Okay, so this is not very surprising, but this is very technical to prove. This is actually, okay, this is what I'm going to put under the carpet, but this is what we have suffered on. Okay, so this is a big part of our result, but I think it's kind of reasonable. Okay, and what's on the board and what's in there is not exactly the same thing. What's on the board, it would correspond to having the quantifier in M inside the probability. Okay, but via union bound, it doesn't change much, okay? Putting the quantifier outside, you just gain a factor log u, and you can put this log u into the epsilon. Okay, so these two things are effectively the same. Okay, so why does this? Why is this lemma important? Well, it kind of gets us one step further in our quest, because now it allows us to identify one event which is much more likely under the size bias measure than under the original measure. So take M as in the lemma, okay? M, which is M that corresponds to some given U. Then what you have is that, well, the probability that Wm is larger than U under the size bias measure, well, by definition, it's equal to this. Now, on this event, Wm is larger than U, so you can just replace Wm by U if you want a lower bound. And this U in front, it takes off the power -1 here, and so you get the lower bound here is U to the minus epsilon. And okay, from Markov inequality, basically because Wn has expectation 1, you know that this probability is smaller than U to the -1. Okay, so here, I mean, okay, you have to think about U as large. So both events have, okay, under the two probabilities, the probabilities are small, but here it's much less small than here. Okay, so building on this, we want now to construct an event which has large probability under the size bias measure and, well, okay, yeah. Large probability under the size bias measure and small probability under the original one. Is that clear what we need to do last?
May I ask why you have the inequalities greater than U to the minus epsilon?
Oh, I'm using the lemma. The probability is larger to U to the -1 plus epsilon.
Okay.
And then I have a U in front.
Okay, thank you.
Yeah, so yeah, this kind of tells you that why -1 cannot be the answer. Like you cannot have -1 here in this lemma because this would give you a constant bound. Okay, but having something close to -1 is very good because when you look at size biasing, you get +1 automatically.
So should we think of epsilon as a smaller here?
Yes, I mean, the smallest epsilon is, the better your lemma is. You have a lower bound, and the better your lower bound is. What you're losing on is the constancy. The constancy gets larger when epsilon is. Okay, so now let me get you to the last step. And so I have to introduce what the event is. Okay, so I'm going to consider U to be equal to n to the 4d. And I'm going to consider the event A, which is the following. So I want that for all z k in 0 n minus 1 times minus n to the d, theta k z, maybe it's kz here, of Wm is smaller than, no, A is there exists, and this is larger than n to the 4d. Okay, so the event is basically that somewhere in a big cylinder, the partition function of a small system, so m is equal to m of u. Okay, this is the m for the lemma, so m is of order log n. Okay, because mu is of order log u. Okay, so now I'm looking within my system for a starting point where from which the partition function of a system of size m would be big. Okay, and if I look at the probability of A, well, this is smaller, sorry, this is a curly A. This is smaller than, well, I can use a union bound. So I look at the various k's and z, so I have, okay, sum over kz. times the probability that theta kz Wm is larger than n to the 4d. This has expectation 1. So this is smaller than n to the minus 4d. And then I have n times 2n plus 1 to the d. Okay, and well, this decays, okay, this is decays like n to the power minus 3d plus 1. And if you go back to what I said, this power is enough for us. Okay, and if it was not enough, I would choose something bigger here. This is not a big issue. Okay, so now the question is, how do you prove that under the size bias measure, A is very likely? And for this, you have to try to understand what the size bias measure does. So, okay, if you look at Pn, well, it's Wm dp, and you can rewrite it as, well, 1 over 2d to the power n times the sum over x in omega n times exponential of beta h x minus n lambda beta times dp. Okay, and now the point is this thing here, if you fixed x, this is something that has expectation 1. Okay, so you can consider this as a probability density. So really, you can say dpn, it's really 1 over 2d n sum over x in omega n dpx, where this thing is a probability whose density with respect to p is this thing. Okay, now p is a product measure. Okay, the omegas are IID. And this exponential here, it's the exponential of the sum of omegas, so it's a product function. So what you are doing here is you're not modifying the product structure. So you still, under this measure, your omegas are still IID. What you are doing here is you are changing the distribution of the omegas along the trajectory of x. Okay, so things are still independent, but the distribution is different from sites that are on the trajectory of x and sites elsewhere. Okay, and the way the distribution has been changed is just, well, the distribution of omegas on the spine well, it's okay, it has been changed in this manner. Okay, the details are not really important, but okay, so now this thing is going to help us. Basically, you want to say that. So now I'm going to cheat a little bit, but not much. Yeah, you know that this thing, okay, under the size bias measure, it's much more likely. However, here you are starting from a point which is not the origin. So you're not looking at things under the size bias measure for this starting point, but you're looking at under the size bias measure. Okay, so, but the thing is that you can always, okay, for every n, for every k here, you can always choose z which is equal to xk, where x is the trajectory along which you have modified things. Okay, and if you do so, what you see in front of you, okay, during the next m steps, is a system of size m equipped with the size bias measure. Okay, because what you see in front of you is really an IID environment which has been tilted along a random walk. Okay, and the random walk, as you see in front, it's independent on the way you have chosen your starting point, just because of the Markov property for the random walk. And you can say the same for the environment. Okay, so this is the idea. So the idea now is to say, okay, if I look at Pn of A, C, well, this is smaller than the probability that for all, okay, so for all j, such that j plus 1 m is smaller than n, theta jm x jm wm is larger than n to the minus 4d. Okay? I mean, I want things to happen for every k and z, so here I'm just taking a subset on the spine. Where I'm obviously cheating is that there is no x when you look at the environment. But this is just really a matter of introducing the right notations to make sense of this. I'm not cheating by a lot. Okay, now this thing, now you have everything here is independent. So this, okay, and this is smaller or equal because I'm taking the complement. So maybe strictly smaller. Okay, and this is, okay, the number of terms I have here is basically n over m, okay, with some rounding. And the probability I have is 1 minus pm wm larger than n to the 4d. Okay, so this is good. Okay, what you get is that this is larger than 1 minus n to the minus 4d epsilon. Okay, this is using the lemma. N over m. Okay, and remember that m is log here. Okay, so you just take epsilon is equal to, say, 1 over 8d. And you're done. Basically, you have 1 minus 1 over square root of n to the n. Okay, so things decay really, really fast. Okay, so I'm just on time. So thank you very much.
Questions?
What happens with the environment is not bounded. If all exponential moments are finite, it's like the same. But can you imagine some situation where actually you see the phase transition to strong?
No. Okay, so
Repeat the question.
Okay.
Hubert, they didn't listen.
Okay. So the question is the assumption about boundiness of the environment important? The answer is no. And for instance, if you look at this lemma, we have now a proof, which is on the archive, that this thing is actually true also if you have exponential moments. Okay, so here it's look like boundiness is important. Not really. If you have all exponential moment for omega, this is good enough. And okay, boundedness is used a lot in the proof of this lemma. And again, we haven't tried very, very hard because initially we thought it was too hard. Also, we haven't tried so hard because we wanted to write the result first in the bounded case because the proof is already quite technical, so adding technicality over technicality was not the point. But yeah, it seems that even without modifying the structure of the proof, we could relax this assumption. Okay, it's not something crucial. What's crucial for this result to hold is some assumption on the random walk, on the underlying random walk. So if so, let's say that you do not consider nearest neighbor random walk. Okay, so if you consider random walk, if the increment of the random walk decays like a power of the distance, okay, if the probability of going at distance L decays like a power of L, then that's good. But if you have a random walk that can possibly make really long jumps, then you can run in. It has been proved explicitly that you can have you can be in cases where there is a phase transition from weak to strong disorder, but there is no very strong disorder regime. Okay. So this is part of the PhD work of Roberto Viveiros. Okay, who defended his PhD here 4 years ago. So, yeah, the result is true with a big degree of generality. You have to take very spread out random walk for it not to be true. There is something which we use, which is a bit specific, that is, that does not hold for every random walk. So, yeah, what happens at the critical point, okay, here, yeah, okay, I believe it's true with full generality, but there are some cases where we would not be able to prove it. Like, basically, we would not be able to prove it for ZD, where D is strictly between 2 and 3. Okay, so like for transient walk, but that are less transient than Z3.
Any chance that one can do the same on a Kelly graph, for instance, nearest neighborhood walk, but on a graph which is not ZD, but is the graph of a group, another generated group?
Okay, so I just told you about very spread out random walk. Basically, if you have a Kelly graph, either it has polynomial growth and then it looks very much like ZD.
Yeah, this is a theorem.
Yes. And in that case, you can do things. If it's not, then it really enters this class. Like the fact that the balls grow like powers of n is really important here. Okay, so this is kind of this is what the assumption of the random walk I was telling you. Like the essential support of the random walk after n step is something which is the power of n.
I think the theorem of Kelly graph is that if the growth is bounded by a power, then it's exactly polynomial.
Yeah. Yeah. And okay.
So, do you have any insight of what should be the scaling limit at BC, at beta C?
Well, the scaling limit is of the partition function is the partition function itself because it doesn't go to zero.
Of the polymer.
Oh well, you have weak disorder, so it's Brownian motion. Yeah, no, the question is more, is there anything which is specific at beta C? Like, is there some signature of beta C? What happens at beta C a bit different from what happened in the rest of the weak disorder phase? And, okay, I believe there is something which holds, which is, like, if you take the overlap between two replicas, Okay, so this gives you a variable. Okay, under the infinite volume measure. Okay, if you so you take then this has exponential moment of positive order if you are below beta c, and this does not hold at beta c. So it probably has a power decay at beta c. But these are very fine properties. Like I guess typically, yeah, you have really to look at rare events to make a difference between the two.
Could I ask a question?
I think the micro
Maybe a simple question. Can you vary beta with n? Can you take beta c plus something small with n?
Well,
Is that,
yeah, and say interesting about it. Yeah, the thing is that okay. So this is part of what this result is trying to achieve. Basically, the first step would be try to understand how this behave for u small. Okay, and then take okay, probably take un such that this thing is equal to 1 over n, and try to see if you see something interesting. Okay, because these things tells you that this is the scale on which things vary, and I don't know. Perhaps you have to. I don't know if this is exactly this that you want, but yeah, this is probably the right thing to do. Yeah. Look at things at the correlation length, so it's the inverse of, take n to be the inverse of the free energy. But the first thing to understand would be, how does this behave? Okay, does this behave like a power view? Is this much smaller? And yeah, for the moment, it's difficult to understand exactly this.
Any other question?
Oi, Hubert, eu posso fazer uma pergunta?
Claro.
Claro, Shanti.
Hubert, yes. So, could I ask you to explain a bit the intuition for the V disorder why we expect the Brownian motion for the rescaled element? I mean, for those who never learned the random polymer.
Well, okay. It's really a really refined statement, but there is a way to understand at least part of the result. Okay, you have so the polymer measure, it's like one. Well, okay, you have P n beta. It's of something. It's 1 over Wn times the sum. Okay, but okay, you can define a non-probability measure by just ignoring Wn. Okay, and apparently it should not be very different because these things converge to something which is positive.
Okay.
Okay, so you can expect that the expectation of mu n beta and the expectation of p n beta are about the same. Okay? And the expectation of mu n beta is exactly p. Okay, because here you're averaging the Gibbs weight, and the Gibbs weights they have expectation 1. Okay. So okay, these things you can make it rigorously, and basically it tells you that this measure here is absolutely continuous with respect to the random walk measure. Okay, so therefore all moisture properties of the random walk are conserved. Okay, and this is the first step to prove the diffusive behavior. Okay, but I mean, for instance, this already gives you for free that the trajectories don't go further than square root of n and things like that. So.
Okay.
So this simple argument already gives you something.
Any other question on the web? Well, if not, I think we can thank Hubert.